In Chapter 5, we're going to introduce an important topic in linear algebra, as well as many other kinds of math, and that is eigenvectors and eigenvalues. The basic concepts presented here, that is eigenvalues and eigenvectors, are useful throughout pure and applied mathematics, and there's lots of different applications in difference equations, continuous dynamical systems, as well as things in graph theory and combinatorics. They provide critical information in engineering design, and they arise naturally in such fields as physics and chemistry. These ideas are very important, not just in this course, but in many fields across science and math. So let's look at what an eigenvalue and what an eigenvector is with this first example. Let A be the 2 by 2 matrix, 0, -2, -4, 2, and we're going to examine two vectors, u and v. Let's examine the images. Remember, images means what happens when I multiply by A to u and v. So if I first take AU, I take A multiplied by u. Remember, we're taking the first row times the column. 0 times 1, -2 times 1 gives me a -2. And then the second row times the column. -4 times 1 times 2 times 1 is -2. And I'm left with the vector -2, -2, which I'm going to write as -2 times the vector 1, 1, because I want to make clear that this is the same as -2 times my original vector u. And when this happens, we say that u is called an eigenvector of A because we have AU is equal to lambda u for some lambda in R. In this case, we had lambda is -2. Opposed to that, we have AV. When we do that multiplication, we're left with -2, 6, and that is not a multiple of V, V being -1, 1. If it were a multiple, it would have to be times 2, because -1 times 2 is -2, but it doesn't work for the second entry. So therefore, we say V is not an eigenvector of A, since AV is not a multiple of V. So if we think about this graphically, here is a picture of the vector u. And when we multiplied it by A, we were left with a multiple of u, -2u, and that was the same thing as A times that vector. As opposed to V, when we multiplied by A, we're left with something that's not on the same line as V. In this case, we have something up there. So an eigenvector is going to be something that lies on the same line as the original vector. It's a constant multiple of that vector. The definition, making it formal, is an eigenvector of an n by n matrix A is a non-zero vector x. This idea of non-zero is really, really important, such that AX equals lambda x for some scalar. The scalar lambda is called an eigenvalue of A if there is a non-trivial solution x of AX equals lambda x, and then that x is called the eigenvector corresponding to lambda. Let's take a second and just remember, if we have x equal to 0, then AX equals lambda x for all lambda. This is a trivial solution. This solution is held always. We'd have both equal to 0. A times x would be 0. Lambda x would be 0. The 0 vector, and everything would be okay. So because of this, this is not interesting at all. This is a trivial solution. We are not going to consider the vector x equals 0. So we need a non-zero vector. That is also said that we need a non-trivial solution of that equation. So, looking at an example, we are going to show that 4, in this case 4 is equal to lambda, is an eigenvalue of A, 0, -2, -4, 2, and find the corresponding eigenvectors of that eigenvalue. So first, the scalar 4 is an eigenvalue of A if and only if AX equals 4X has a non-trivial solution. That's the definition. And what we're going to do is we are going to rewrite this equation so that we can solve this as a homogeneous system. So I want 0 on one side, so I'm going to subtract 4x from both sides, just doing some algebra. We can add and subtract pretty freely across an equal sign. And we're left with ax minus 4x. Now one thing that's going to be tricky here is that you may be tempted to write this as a minus 4 times x equals 0. But this doesn't really make sense because what does it mean to have a matrix minus a scalar? So we'll say that a matrix minus a scalar doesn't make sense. We have no way to kind of think about what that means. So we're not going to write a minus 4 times x, but if I introduce the identity matrix in here, that doesn't change the multiplication. If you multiply anything by the identity matrix, it's left unchanged. So if I have ax minus 4 times ix, and then instead I factor out the x, so I have a minus 4I times x equals 0, now that makes sense because now I'm not just subtracting a scalar, I am subtracting a scalar times the identity matrix, which gives me a matrix on its own. So if you want to find ax equals 4x, solutions to that, we are now going to write that as a minus 4I x equals 0, and this is what we're going to think about more often than not. This is a homogeneous system. We are trying to find a solution to that homogeneous system, a non-trivial solution. As the trivial solution always exists. So let's go through it. Let's find this non-trivial solution if it exists, and we'll go from there. So a minus 4I, we take the matrix A, we subtract 4 times the identity matrix, which is going to be 4, 0, 0, 4. You multiply each entry of the identity matrix by 4, and we are left with that matrix there. Do the subtraction, each entry minus each corresponding entry, and we get negative 4, negative 2, negative 4, negative 2. So that is a minus 4I. If I want to solve that equation, a minus 4I x equals 0, I can set up the augmented matrix, the coefficient matrix a minus 4I, augmented with the 0 matrix. Row reduce. The row reduction here would be negative row 1 plus row 2 into row 2. And since row 1 and row 2 are the same, we'll be left with a zeros on the bottom, something on the top, and if I take negative 1/4 row 1 into row 1, then I'm left with 1, 1/2, 0, and then zeros on the bottom. Note that this is a free variable, the x2, as there's no pivot in that column, so therefore we have infinitely many solutions. And note that that means that there exists a non-trivial solution. Back when we talked about homogeneous and non-homogeneous systems, we said that a homogeneous system always has a solution, the trivial solution. So if there's going to be a non-trivial solution, we have to have infinitely many solutions, which means we need a free variable. In this case, I have, if I rewrite this row, x1 plus 1/2 x2 equals 0. Solving for x1, I get x1 is negative 1/2 x2, x2 is x2, and therefore I can write my solution in vector form as x2 times negative 1/2, 1. So let's look at this again. Each vector of the form x2 times negative 1/2 1 is an eigenvector corresponding to the eigenvalue lambda equals 4. So I just want to make clear that there are infinitely many eigenvectors corresponding to one eigenvalue. That is always going to be the case. And let's look at graphically what all of these solutions together would be. Note that we have that all the solutions will be the span of the vector negative 1/2 1. That's what it means to have a free variable times that vector. So anything in that span, anything times negative 1/2 1 will be an eigenvector. If we look at this graphically, here's the vector negative 1/2 1. And if I take anything times that vector, so here is this vector right here. This is negative 2, 4, which is going to be 4 times that vector. And we could do any other kind of thing here. Here we have negative 1 times that vector, and we could do any multiple times that vector, and that gives us the span of that vector, which is going to be all the solutions, or all the eigenvectors corresponding to that eigenvalue. We call that the eigenspace for lambda equals 4. So in this case, the eigenspace for lambda equals 4 is that span. That represents a lot of vectors, infinitely many, and that's everything that's a eigenvector for the eigenvalue. So to go down here real quick, the set of all solutions to that homogeneous equation is called the eigenspace of the matrix corresponding to that lambda, to that eigenvalue. And then a quick warning, this method that we're talking about cannot be used to find eigenvalues. Remember, in the very first part of this example, we were given an eigenvalue, or we said to show that lambda equals 4 is an eigenvalue, then find eigenvectors. We cannot use this to find the eigenvalues. We will have a way to find the eigenvalues in section 5.2. So let's do another example here. Let's let A be the 3 by 3 matrix, 2, 0, 0, negative 1, 3, 1, negative 1, 1, 3. An eigenvalue of A is lambda equals 2. Remember, we're not going to be finding eigenvalues in this section. We're going to be given it. And the question asked, write the eigenspace as a span of vectors. That means we're going to find all eigenvectors corresponding to lambda equals 2. That's what it means to find the eigenspace. So we're going to write it as a span of a vector or vectors. So if I want to find the eigenvectors, I will be solving the equation a minus 2ix equals 0. So first what I need to do is find a minus 2i. If I take 2i, remember I'm taking 2 times the identity matrix, that'll give me 2's along the diagonal. That's what 2i corresponds to. And if I take a minus 2i, I'm just going to look at the diagonal entries. That's the only thing that's changing. I'm going to be subtracting off that 2 in each of these cases. And I'll be left with a 0, 1, and a 1 on the diagonal. When we do this a minus 2i, only the diagonal entries are going to be changing. Everything else is left unchanged. So now I have this homogeneous system. Now we're back to a 1.4 kind of problem. And we are going to solve this homogeneous system by row reducing. The row reductions are going to be swapping 2 rows and then adding 1 row to another and then multiplying by negative 1. And we'd be left with this row reduced matrix. Remember, this is in row reduced echelon form. And note that in this case we have x1 is equal to x2 plus x3. x2 is free, and x3 is equal to a free variable. So because there are free variables, we have a non-trivial solution. If we didn't have free variables, we would not have a non-trivial solution, and this would not be an eigenvalue. But we do have that, so we're in the clear. And since there are two free variables, this is going to affect what the eigenspace is going to look like, and we'll see that in the next line here. So the vector x is x1, x2, x3. We've written x1, x2, x3 in terms of the free variables, so we can write that as x2 plus x3, x2 and x3, and then writing it as a parametric equation of vectors, or a vector equation, we can write this as x2 times that vector plus x3 times that vector. So now let's finish the question. Let's write the eigenspace as a span of vectors. Because we had those two vectors multiplied by the free variables, we can say that the eigenspace is equal to the span of those two vectors. And note that we can't write this span any nicer because those are not multiples of each other. This is exactly what we have. This is a plane in R3. That's what it looks like graphically. And any vector in that span is an eigenvector corresponding to lambda equals 2. Again, that is infinitely many. Anything in that span, any linear combination of those vectors will be an eigenvector. So I could take maybe -2 times the first plus 3 times the second. And that will just give me one of my eigenvalues. In this case, that would give me 1, -2, 3. There's nothing special about that eigenvector that I found, but we could find any eigenvector in that way. I want to take a quick second here and talk about if I have a minus lambda I x equal to 0. That's what I'm trying to solve. If lambda is an eigenvalue, then this means that there are non-trivial solutions to this system. And we saw that in our big theorem in the inverted matrix theorem, that if there are non-trivial solutions to a homogeneous system, this gives us a lot of different characterizations of that matrix. One of them being that A minus lambda I is not invertible. Another word for that is that it is singular. And we are going to use that fact in the next section to know that A minus lambda I is not invertible. If lambda equals an eigenvalue, if that's an eigenvalue, then we have that this is a singular matrix. And that is if and only if that's the case. If there is only the non-trivial solution, if there is only the trivial solution, then A minus lambda I would be invertible, and that would not allow us to have infinitely many solutions, and it wouldn't be an eigenvalue. Lambda wouldn't be an eigenvalue. So let's look at a different kind of example now. Let's suppose that lambda is an eigenvalue of A. Let's determine an eigenvalue of A squared and A cubed, and in general, A to the n. There's just going to be a little trick that we're going to do in this calculation to find this answer. So since lambda is an eigenvalue of A, there is a non-zero vector x such that ax is equal to lambda x. And since I'm trying to find something about a squared, I'm going to multiply both sides of this equation on the left by a. This will give me a squared x on the left, and then I can factor out the lambda out in front. It's a scalar, and I can write this as lambda ax. Now the one little trick we're going to do is that I can rewrite ax. Remember, I have ax is equal to lambda x, so I'm going to use that fact to rewrite ax as lambda x, which is the same thing as lambda squared x. And now I have this new equation, a squared x equals lambda squared x, which means that lambda squared is an eigenvalue of a squared. Going back to the one trick we're doing is that since I'm multiplying by a again, I can rewrite this ax as lambda x again to get an eigenvalue. Let's do the same thing with a cubed. Let's show that lambda cubed is an eigenvalue of a cubed. Again, same trick. I'm going to multiply by a on both sides of my new equation. Take the lambda squared out in front on this side. And then I have ax. And note that ax again is equal to lambda x. So I'm going to get lambda cubed as an eigenvalue. A cubed x equals lambda cubed x. This scalar is the eigenvalue. And in general, we're going to have that lambda to the n power is an eigenvalue of a to the n power. One last theorem here. We're going to talk about triangular matrices. The eigenvalues of a triangular matrix are the entries of its main diagonal. Remember that we introduced what a triangular matrix, we had two kinds, the upper triangular and lower triangular. What that means is that you have zeros below the main diagonal or above the main diagonal in those cases. This is an upper triangular matrix because everything above or below the main diagonal is 0. Everything else is could be anything. So let's look at this case, the 3 by 3 upper triangular case, and we're going to examine the eigenvalues of that matrix. That means we're going to look at a minus lambda I. So I have my matrix. The only thing that changes when I do lambda I is going to be the main diagonal. I'm going to get the main diagonal entries minus lambda are the new main diagonal entries. Everything else is left unchanged. And we can go back to the definition. We say that lambda is an eigenvalue of a if and only if a minus lambda ix equals 0 has a non-trivial solution. That means that a minus lambda I is a singular matrix. It's not invertible. And again, this is going to occur if and only if a minus lambda ix is equal to 0 has a free variable. We can look at this matrix and we can see, since this is in an echelon form, we can see when is this going to have a free variable. And that is going to occur when the main diagonal entries are 0. That will create a column without a pivot if I have any of those main diagonal entries 0. So this will occur when a11 minus lambda equals 0, or when a22 minus lambda equals 0, or when a33 minus lambda equals 0. And again, that means that a11 will be an eigenvalue, a22 will be an eigenvalue, and a33 will be an eigenvalue. So if I have a triangular matrix, this is the same for a lower triangular matrix as well, the main diagonal entries, A11, A22, and A33, are my eigenvalues of the matrix. So in this section, the most important thing we did is talk about how to find eigenvectors. In the next section, we're going to talk about how to find eigenvalues of a matrix. And putting those together, we can then find eigenvalues and eigenvectors of the matrix, which is the goal of this Chapter 5 material.